Swayam Prabha. Digital India. Educated India.
Okay, welcome back, and let's continue the discussion on the turbulent flow. And we are looking at different situations. So, first we started off with the incompressible Navier-Stokes, and where density is constant and the viscosity is constant. Then we moved to a situation where still the dynamic viscosity is constant, but there is a variation of the density, which essentially gives rise to some effect due to density, and we approximated that one with the Boussinesq approximation. This is what we got it. Basically, when you have the Boussinesq approximation, then where you have effect of the density variation, and the density variation is only a function of temperature. So, you got your continuity, momentum equation. Now, momentum equation will retain a term which is due to the temperature, and this is my energy equation in terms of temperature. So, this term is known as buoyancy effect. So, this is nothing but my first order effect of weak temperature induced density variation. Okay. So, that is what you get for Boussinesq approximation. So, that is, we have already looked at this picture at different situation. This is a picture where your laminar transition, and this is a turbulent flow. This is a flow over a perforated flat plate, and these are jet flow. This is RE1, this is RE2, which is greater than RE1. These are the jet flows. Now, if we combine or accumulate all these characteristics that we have discussed so far, then we can see this is unsteady, the flow, and 3-dimensional. Okay. So, that is quite obvious. This flow field has to be completely unsteady and 3-dimensional, and when it is unsteady and 3-dimensional, we can say it is quite chaotic and irregular in nature. Then we can characterize it by lot of eddies. These are the eddies in every flow you can see, but they have different scales. Sometimes they are large scale, sometimes they are of small scale, and there could be a wide range of scales, and that depends on the Reynolds number, what kind of scale we have, whether it is a multiple scale or single scale or something like that. Then, as I said, there are multiple length scale. Primarily one could be large scale, which we term as macrostructure. There could be small scale, which we term as microstructure. So, that is, I mean, combinedly all these features that are exhibited due to unsteady and 3-dimensional flow field. Then also the flow field is at high Reynolds number. So, there is a scale similarity, that means the large scale structure are independent of Reynolds number. So, if you look at the large scale structure or the macro structure, they are independent of the Reynolds number, that gives you a scale similarity. This is an very important characteristics. Then there is dissipative in nature, the flow field is dissipative in nature. So, that means there is a rapid loss of energy and is effective in mixing and mass, momentum, heat, etc. So, these are the characteristics that we have seen. Now, we have already said that for turbulent flow, the Navier-Stokes equations are ill-posed, that because if we make some small perturbation to the initial condition or boundary condition, the flow does not remain any more stable. So, this is the where we can use our concept or linear stability to see whether the flow is stable or not for some small perturbation, because this is quite important to identify the zone where you can see the stable flow field and the zone where it is unstable. So, we can do some analysis for inviscid flows, that means no viscosity. One could be type of Kelvin-Helmholtz instability, this is an image of unstable jet flow. So, this is an image of KH instability or Kelvin-Helmholtz instability. Then we can look at Rayleigh stability equation for 1D basic flow and then inflation point criteria for instability. Now, similar exercise can be extended by including the viscosity. In that case, we will get Orr-Sommerfeld equation and we can find out our stability diagram. So, the types of stability analysis one can do. So, if we start right bottom here, the analysis, let us say this can go to one direction where it is a nonlinear. So, which is something called finite amplitude disturbance. Or other one is the segment where we can say it is a linear, that means infinite simal disturbance. Okay. Now, we will do or restrict our analysis for the linear system only. So, this one will not going to be discussed. So, we look at only the linear stability system. Now, there are also different approach of this. One can look at either normal mode analysis, which is no interaction between Fourier mode. So, that is normal mode analysis, or it could be non normal mode analysis, that is mode interaction. So, even under the basket of linear stability analysis, we will only be doing the normal mode analysis. We will not treat this non-normal mode. So, not treated here. Now, under the normal mode analysis, there could be two categories. So, we will say 1D basic flow, either it could be inviscid, which is essentially Rayleigh's equation, or we can do viscous, which is or Sommerfeld equation. So, we will look at these two type of instabilities. Now, before doing that, we can look at some of this concept of a linear stability analysis. So, first thing that one has to do, formulate the base flow or basic flow. So, which is usually stationary and laminar, that is then you can superimpose on this a small in stationary disturbance, that is u prime. Then you can substitute the sum, which is plus into Gavrani equation and linearize like del u prime by del t and so on. Finally, from that linearized equation one can formulate an eigenvalue problem. So, this is quite important, and then we can find the non-trivial solutions, which is for a non-zero disturbance. And then finally, the flow is unstable if a solution grows in time. So, that is how we can do that. So, we start with a kth instability, which is linear and inviscid analysis in nature. So, we can have a field like this, and this is lambda. So, this is my state 1, row 1, u1. This is how I defined x and y. This is u2. This is my gravity 0 and state 2, row 2. This is eta xt. This is my CR. Now, here some definitions which are quite important to note. One is that k equals to 2 pi by lambda, which is wave number. Then we get this is WR plus IWI, which is a complex. Then where this is my growth factor, and CR is WR by K, which is lambda by T is the wave. Now, if you look at the base flow or the basic flow, they are y less than 0, you have U1 P1, y greater than 0 U2 P2. Now, if you look at the disturbances, then they are U prime, V prime, P prime, eta. Now, for normal mode analysis, my eta xt is a e to the power I kx minus omega t. So, this is the set of variables that now we can derive the governing equation. So, here we are talking about cage instability. So, we derive the governing equation. Now, for flow with no viscosity and irrotational, which is an Kelvin theory. This is an flow, essentially it is an potential flow theory. Which gives you U equals to del phi by del x, del phi by del y, and Bernoulli's equation will give you del 2 phi by del x2 phi by del y2 equals to 0, and the other term del phi by del t plus half of bar P by rho plus GUI equals to 0. So, that is what we get. So, what is our basic flow? Is stationary plus spatially uniform except for jump at y equals to 0. So, the Bernoulli's equation yield for this half of u1 square plus p1 by rho 1 plus gy equals to c1 and half of u2 square plus p2 by rho 2 plus gy equals to c2. So, this is what we wrote. So, this is constant. So, then for stationary the unsteady term goes off, and from the rest of the term, if it is spatially uniform except the point y equals to 0 exists, and one can also note that the basic pressure varies with height, that is due to gravity, which means C12 are constants. Now, we can formulate the linearized equation for disturbance. So, still we are doing cage instability. This is linearized equation for disturbance. So, from mass conservation equation, we get two equations. One is del 2 phi 1 prime by del x 2 plus by del y 2 equals to 0. Second is del phi 2 prime by del 2 phi 2 prime by del y 2 equals to 0. So, these are the two equation, linearized equation that we get for the mass conservation. Now, similarly, momentum conservation we will get two equation. So, one is del phi 1 by del t u1 del phi 1 prime by del x plus p1 prime by rho 1 plus g eta is 0, del phi 2 prime by del t plus u2 del x p2 prime by rho 2 g eta equals to 0. So, these are the two equation. These are So, from mass conservation there are two equations, from momentum conservation there are two equations, and they are linearized equations, and these equations are for disturbances, Now, we need boundary condition which are quite important. Number one, we can have zero velocity disturbances far from interface. That means one can write limit y tends to plus minus infinity delta phi 1 prime 1 or 2 is 0. So, that is our zero velocity disturbance far from the interface. Second, we can have kinematic interface condition. So, kinematic interface condition talked about fluid parcels sitting on the interface move with the interface and no gap should be formed between the two fluids, which means d eta by dt equals to v at y eta del phi by del y at y eta. So, that is my kinematic conditions. And last is dynamic interface condition. When surface tension is neglected, normal stress must be continuous across interface. Now, for inviscid flows, a continuous normal stress reduces to a continuous pressure across the interface, which will get at y equals to eta, get P1 equals to P2. So, this is what we get. So, these are three conditions that one have as an boundary condition. So, we stop here today and continue it in the next lecture.